Hello everyone and welcome to the week 11 of NPTEL course in pharmacognosy and phytochemistry. So in this week as well, we are studying different quality control methods for evaluation of herbal drugs. Just to recollect, in the week 10, we saw organoleptic methods of quality control, we saw macroscopic as well as microscopic methods of quality control, we saw physical methods of quality control, and we started with chemical methods of quality control. In chemical methods, we also saw that the chemical methods could be qualitative, that is, they will tell us what type of compounds are present, and they can be quantitative, telling us specifically how much the compounds are present. So let's just recollect, we saw organoleptic, macroscopic, microscopic, physical, and now we are into the chemical methods for evaluation of drugs. And more specifically, we are done with qualitative method of evaluation. Now we are moving on to quantitative method of evaluation of drug. Now quantitative method, when I say I want my answers in numbers, how much of my drug is pure? Is it 90% pure? How much gallic acid does my galls contain? So it's going to be a number, it's going to be a numerical value, and that will tell me the quality of your drug. So there are different methods to it. So when it comes to chemical method of evaluation, we've already finished qualitative methods such as phytochemical test, we've finished microchemical test, we've done limit test especially with respect to heavy metals, as well as thin layer chromatography to check whether the standard or the marker compound is present or not. In this session, we will focus more on quantitative tests. When we are doing the quantitative tests, we are going to assess different spectroscopic as well as chromatographic methods to quantify the drugs, especially the phytochemicals. This includes your UV-Vis, spectrophlorometry, HPLC, HPTLC, UPLC, GC, and so on. Chemical methods have also been used to quantify toxins such as your pesticides, aflatoxins, as well as residual solvents. So let's dwell into more of your spectroscopic methods in this session. So what is the spectroscopic method? Let's try to understand with a simple example of a UV-Vis spectroscopy. Now in UV-Vis spectroscopy, you have lamp, one corresponding to UV, that is your deuterium lamp, and one corresponding to your light, that is your halogen lamp. So both of this lamp cover a broad spectrum of light, that is from 200 to almost 800, in some cases even 900 nanometers. Now what happens is this lamp then passes through a collimator where your parallel beam of light is taken, and then it is passing through a prism or grating. Now this white light splits into a spectrum after it passes through a prism or grating. Now depending upon my analyte, at which wavelength I want to analyze, I will set it as using a grating. Once that is done, the selected wavelength of light will pass through my sample. If my sample absorbs, so if it is called as the absorbance value. So per mole how much it absorbs is kind of called as molar absorptivity. So I'll put a specific content or a specific concentration of my sample, say 100 microgram per ml, and I will check its absorbance value. Now when I do that, maybe as an output, what I'll see here is you will see something like this. That is you will see a UV spectra and you will see an absorbance reading. Now this absorbance reading will tell me how much quantity of my substance is present. So this is in brief what we do in our spectroscopic methods, and let's now understand how we apply the spectroscopic methods to our analysis, especially quantitative analysis of phytoconstituent. Now take for example, we will start discussing about UV, about absorbance value with respect to a very simple compound such as flavonoids. Now We say flavonoids typically contain a flavan nucleus, which is phenyl benzogamma pyrrole nuclease. And when you saw the flavonoids chapter, if you remember, we put your ring A, ring B, and later on the ring A and B fuses to form your ring C. Now if I split this molecule from here, what I observe is I get what is called as a typical cinnamyl moiety. Now this cinnamyl moiety represents to your phenylpropanoid moiety from your biosynthesis. So this is like your 1, 2, 3. So in addition to your phenyl, you have a C3 additional, and that's why we call it as your cinnamyl moiety. Okay. Now in this side, if you see carefully, you just have a plain phenyl or a benzene ring. Okay. Now this phenyl ring and a cinnamyl ring or conjugation, when I compare in UV, what is important is the wavelength of a substance or a wavelength of a compound depends on the nature of single as well as double bonds. So single bonds mostly absorb in the UV region, whereas if you add conjugation, as you saw in carotenoids, more the conjugation, more colored they become. So in a similar manner, there is a rule, or there are certain rules which can be applied to the compounds, and these are like your Woodward-Fisher rule. So when you do that kind of addition, you can predict what wavelength your compound will absorb. Now if you see carefully, if I break this into two, you will see that the number of carbons and the number of double bonds on this side is higher, and especially more important are alternating or conjugated double bond. So you can see them very nicely in cinnamyl, which has about 3, 4, 5 double bonds, and all of them are conjugated. And then you compare it with A, which have 3 conjugated double bond. So what you see here is the spectra of flavonoid splits basically into two. This part is called as your band 1, and this is attributed due to cinnamyl moiety, and this part is called your band 2, and this is attributed more to your phenyl moiety. So you will see most of the band 1 is because of your B ring and partially due to C ring, whereas your band 2 arises from your A ring. Now if you see carefully, you will see most of the flavonoids showing this pattern. So depending upon what UV maxima your band 1 and band 2 is, remember your band 1 is always going to be a longer wavelength. So band 1 of anthocyanins goes as long as in your colored range, and that is the reason you will see most of the anthocyanins pigments are colored, your flower petals, and your band 2 still stays in your UV region. Your orones, it's about 380 to 430, chalcones 340 to 390. There is definitely some overlap, but not a complete overlap if you see it carefully. Flavin 3 hydroxy substituted or 3 ols, when the 3 hydroxy substituted by a glucosyl. In that case, you will see it shows a band 1 at 328 nanometers and 360 nanometers, or between this range. But when the 3 hydroxy is free, like you saw here, in this case the 3 hydroxy is free. In case of routine, what happens is your sugar is attached. So when the sugar is attached, you get somewhere 328 to 360. When it is free, you get a slightly higher wavelength out there. But your band 2 remains the same because that side is not involved clearly in any bond formation. Similarly, you can have your flavones, which show a band 1 between 330 to 350, flavanones between your 300 to 330 nanometers, isoflavones. Now isoflavones show a slightly what is called as shoulder peak. Now what is shoulder peak here is, if I say my flavonoid absorbs something like this. In case of isoflavones, what is going to happen is my spectra, now this is the absorbance, this is the lambda. So I am just putting, in that case what is going to happen is this is definitely going to come down in the same way and rise at about 250 nanometers, but my band 1 is going to be a tiny thing, it's not going to rise up, and that's the reason this is like as good as a shoulder and it is called as your shoulder peak. So for isoflavones, your peak, especially your band 1, is converted into a shoulder peak. Now, how do you use this data for quantification? Now, this quantification I can use, or I can set my UV spectrophotometer at a UV maxima corresponding to that particular flavonoid band 1 and band 2, and I can measure the concentration. Say for example, I say my quercetin is giving me an absorbance value at 0.8 for 100 microgram. If my sample is also giving the 0.8 value, that means in my sample also quercetin is 100 microgram. But this is not as simple. Why? Because your flavonoids don't occur singly. In plants, they occur with different other constituents, and many of this constituent also absorb in a similar range, that is 320 to 380. So even saying that your band 2, especially this one, and band 1 are very peculiar of flavonoids, that doesn't assist me when I am doing quantification from the plant extracts. If I am doing the quantification of pure actives, pure quercetin, definitely I can directly use this, but when I am using plant extracts, because other compounds are interfering, I will have to create some colored complex. So what do? I create colored complex with metals. Now imagine some metals like your aluminium, okay? Imagine some metals like your aluminum. So in this case, what is going to happen is your Al will try to chelate itself. Now Al is like a 3 positive, right? So it will try to chelate with a negative. So it forms a kind of complexes, and this complexes then polymerize. See, all the 3 valencies are not satisfied. So what is going to happen? It is going to take another hydroxy also, probably this hydroxy of the next flavonoid, and it gives a nice structural attribute to that, and which gives in a formation of nice blue color complex, and that blue color complex I can quantify it. So on initially I had my band 1 here at 360, I had my band 2 at 250 nanometers. But the moment I add my aluminum chloride to it, what do you see? What happens to the wavelength is called as bathochromic shift. That means it now absorbs at a slightly longer wavelength. So now it is absorbing at 425 nanometers instead of 630. What does that do? Now that moves my wavelength from a UV or near visible to almost a good colored wavelength, and that is the reason why I will get more accuracy when I measure it in this, because all my compounds are not going to absorb in this region. Majority of them absorb between 200 to 350 nanometers. So that major chunk, when it's taken care of, I can selectively get my absorbance of flavonoids at 425 nanometers. Similarly, I can use other metals, I can use iron, I can use your tin, I can use your zinc and other metals and so on. So it forms complexes with most of the metals and give you colored complexes. The color with aluminum chloride is more predominant and lasting. So how do you do this? In this particular test, when I have to quantify or I have to carry out a total assay, assay means quantification of flavonoids, I can do it by preparing my sample extract. Now when I am preparing the sample extract, the most important concern for me is which solvent do I choose. Now when we did chemical tests for flavonoids, if you recollect, a very good non-specific solvent for extraction of flavonoid, both glycones as well as the glycosides. So glycones as well as the glycones can be, or that is the glycosides, can be extracted using ethanol as a solvent. So I'll take 1 gram of drug and I'll probably boil it with about 100 ml of sample or so, and I'll start preparing a stock or a sample stock. Okay. So I'll take this sample stock, and this sample stock I'll take about approximately in this range. Now this range is taken for this particular assay that I've used, but depending upon the flavonoid content of your drug, this value may vary. Say for example, when you say Sophora, which contains 20% flavonoids, You know that whenever you have to do quantification by UV, you have to have the reading less than 1 absorbance, and it is said that less than 1 absorbance perfectly aligns with the Beer-Lambert's law, where absorbance is proportional to concentration. But when you move on the higher side, that is absorbance value more than 1, the Beer-Lambert law deviation start. So we don't want that to happen, and depending upon the drug, this value is optimized. So you'll just take about 0.5 ml of a given value that you can decide depending upon the flavonoid content, then some amount of alcohol to dilute it, and then you add your reagent. Your reagent is required in a very small quantity, that is just 0.2 ml of 10% aluminum chloride and about 0.2 ml of your buffer, that is your potassium acetate. You dilute it and let it react. Now what is going to happen is, when you let it react at 30 minutes or when you let it react for 30 minutes, you will see that slowly the solution is turning bluish in coloration. In some cases it is even taken into dark to eliminate any effects of atmosphere on it. So once that is done, you compare that with your standard. Now similarly, as you prepared your extract, prepare the solutions with quercetin standard, so that each test tube contain 2 microgram or even 15 micrograms. So somewhere between 2 to 10 to 15 microgram per ml stock you will prepare, and that you will again react with dilute with alcohol, react it with your 0.2 ml of 10% aluminum chloride and 0.2 ml of 1 molar potassium acetate. So when this happens, what is going to happen is, it's going to show you an absorbance value, and we are going to record it. So when you are recording it, say for example you have your 2, 4, this is just I am putting it as microgram per ml, 2, 4, 6, 8, 10 microgram per ml, and this is the absorbance value. Max value what I can go is 1, so maybe I am just putting here as 0.5, 0.25 and 0.75. So I'll start preparing what is called a standard curve. So when I do a standard curve of quercetin, I may get some linearity, that is my absorbance goes on increasing as the concentration increases. Okay, so I might find my spots, or that is 5 spots like this. So when I draw a line through this, this might be almost very linear. Now what happens is, I will check the absorbance of the unknown, that is my plant extract, and say for example this is the absorbance of my unknown. So what do I do here? This absorbance value I'll just extrapolate it back, and wherever it falls, say for example 9, then 9 microgram per ml is the concentration of quercetin or flavonoid in terms of quercetin in the given extract. So that is how I used to quantify. Now if you use any dilution, you multiply it by your dilution factor. So this is how total assay of compounds, especially flavonoids, is carried out. Now moving on to the next one, you can also do the same for your tannins or polyphenolic compounds. Now when I say polyphenolic, polyphenolic includes anything that has dihydroxy and a phenyl group. So this can be a gallic acid or any other compound which contains your polyphenol. So what happens in the Follin-Ciocal-2 method? Now Follin-Ciocal-2 method is a specific method for polyphenols, and this is based on its reaction with what is called as phosphomolybdic and phosphotungstic acid. Again, if you just check plain absorbance of gallic acid, you will get 225 and 265. Like I said, most of the compounds absorb well, and they will absorb below 350 nanometers, and that's why this region becomes very crowded as far as the plant extracts. Now if by some reagents we are able to move the wavelength to a higher side, that is the detection wavelength, that becomes a good method of quantification. So in this Follin-Ciocal-2 method, we add a base. Now this base is generally a sodium hydroxide, or if you want a milder base, you can use sodium carbonate. The intention here is to bring the pH value to about 10. Okay, so pH 10 is what we are looking for, and at pH 10 what is going to happen? These groups are going to become ionized, so that they will react with Na and become ONa. Okay. So they go on becoming ionized, and eventually what is going to happen is when they are ionized, they tend to react with phosphomolybdic and phosphotungstic acid. So when they are reacting with phosphomolybdic acid, phosphotungstic acid, there is a slight change in aromatization. You will see all this alls becoming ones. So you will be seeing lot of quinones, you will be seeing lot of negative charge, and what is going to happen, it is going to release the electron. This electron will convert your phosphomolybdic acid into, I am just drawing it roughly, I am not putting a quantitative balance, but just for your understanding. You know, this 12 I can just split it into 4, and this, so 4 plus 12, eventually it will make it 12, O40. So what is going to happen here is, it's partially oxidizing, so this will remain plus 6, this will remain plus 5. So partial oxidization happens, this electrons go here, change in, and this gives what is the blue coloration. So this happens in an alkaline pH, and that is why it is so important. Now once this reagent is changed to a partially converted compound, in that case you will see that this reagent will now absorb at 750 nanometers. Now this is what correlates with the absorbance maxima, and this is what we are going to use for quantification of your polyphenols, especially tannins and flavonoids, using your Folian-CO-Cal2 method. Again, if you draw a curve of absorbance versus concentration, you will find a good correlation, and definitely you will be able to spot the concentration of the unknown. Now the next method which is used again is a colorimetric method, and that is for determination of steroids. We can also determine, and this is the same test, you remember your Lieberman-Boucard test, this is the same test. What you are going to do is, but you are going to be little selective. So you are going to take your steroid containing drug, you are going to extract it in chloroform. The reason is, if you see your lipophilic compounds, especially your steroids or triterpenoids, they will be more soluble in your chloroform. In some cases where you have to determine the saponins, in that case it is advisable to do the hydrolysis first, so that the sugars are cleaved, and thereafter you are going to extract it in chloroform. In that case, the glycone part of saponin gets extracted in your chloroform layer. Now you are going to take this chloroform layer and dehydrate it. The reason why we dehydrate it, because the presence of moisture kind of retards the color as well as the reaction. So you will treat it with about acetic anhydride. First we will check, in case if it is insoluble, it is always advisable to dissolve it with little amount of glacial acetic acid, but if it is nicely soluble in chloroform, no need to do it. Now you are going to add acetic anhydride, that is almost 19 volumes, and then sulfuric acid 1 volume. So in that ratio when you add it, it is said that your compound gets converted into acetate and then sulfate, and later on what is called as the sulfonic acid. So it kind of dehydrates and releases or causes a lot of unsaturation. This unsaturation later on kind of aromatize. Now in addition to that, what you will get is also a sulfonic acid derivative. So SO3H. Okay. So in this case, when you get a sulfonic acid derivative, now what happens here is this sulfonic acid derivative is, or the sulfated products or sulfonated products give you greenish coloration, and I can quantify this greenish coloration at 625 nanometers. So the amount of sterol present, I do a standard curve, and again I will be able to quantify how much amount of steroids are present in your given sample. Having used chloroform as an extracting solvent, I will be very specific, and as a result other molecules will not form a sulfonic acid derivatives. Now the next one is, in some cases there are molecules which produces fluorescence. A good example of that is your quinine sulfate. So your quinine per se doesn't have much fluorescent property, but if you convert quinine into quinine sulfate, it produces fluorescence. Now what is fluorescence? Fluorescence is when the compound absorbs one wavelength, that is, you can see it is absorbing 317 and 349 nanometers, but it is emitting at a much higher wavelength. So in this case, when it is emitting radiation, it is emitting at about 481 nanometers. So in this case, you have to change the UV. In the UV, we saw that there is a source, that is the lamp. Then you have your collimators, then you have your prism, and from that you are going to choose a monochromatic light through your prism or grating, and that is going to fall on sample. Now that sample will absorb, and whatever doesn't absorb reaches the detector. Okay, that was your UV principle. Now in case of fluorescence, because this is going to be one wavelength, this is going to be, say for example, 317 nanometers. My detector is not going to be set at 317 nanometers. Interestingly, for fluorescence, I will not measure it in this manner. For fluorescence, you know, my compound is emitting, so I can measure it more perpendicular to the incident ray of light, so that whatever this 317 is passing, which is not been used by the compound, let it go this side. So I am not going to put my detector here, I am going to put my detector here, and as a result only the wavelength that is emitted due to the glow, that is emitted due to the fluorescence, will reach my detector, and that is my 481 nanometers. So I will set my spectrofluorimeter, which is modified UV, to a emission wavelength and excitation wavelength. The excitation wavelength is the wavelength which will cause the electrons to excite, and this is your absorbance wavelength, that is, say for example 317, and then emission wavelength is what the molecule is emitting. In this case it is 481. So again I can do a curve, but in this case what I will do is I will check the fluorescence instead of absorbance, and this is going to be a concentration. So as the concentration increases, the fluorescence also increases. Okay, and then I can quantify by unknown by saying that my unknown shows this amount of fluorescence, so as a result its concentration is going to be this much. Okay. So here are few references to different spectroscopic methods for analysis of the compound. So they are huge numbers, but yes, apart from that, your pharmacopoeias and your quality control books on WHO also give you these methods. And thank you everyone for your patient listening.